This is the Brennan Monorail, a train from the early 1900s that seemed to defy the laws of physics. Not only did it stay perfectly balanced on a single rail, but it also leaned into corners automatically, with no driver input. This was a real invention, unveiled in 1910 by its creator, Louis Brennan. The concept behind it was simple. Using a single rail instead of two would make trains faster and railway construction cheaper. Brennan's train could navigate curves at high speeds without derailing, and its tracks required half the materials of a conventional railway. Unlike modern monorails, which have elevated tracks, Brennan's design could run on existing railway lines. While it may appear unstable, it was actually engineered for balance. At the core of this train was a gyroscope, which corrected its tilt before passengers even felt it. This was a revolutionary feat of engineering, especially for 1910. But how exactly did it work? We studied Brennan's patents and built a detailed model to reveal just how brilliant this design truly was. To understand this, we first need to explore gyroscopes. When a spinning disc has angular momentum, it resists tilting and tries to stay stable. If you attempt to tilt it, it starts rotating on the vertical axis, a phenomenon called precession. However, if you force it to precess instead, the disc tilts in the opposite direction. This property allows a gyroscope to naturally return to equilibrium. Brennan realized that this principle could stabilize his train, so he conducted experiments by placing a small flywheel inside a model train and powering it with an electric motor. Initially, this worked. The gyroscope kept the train from falling over, but there was a major issue. When the train turned, the gyroscope didn't turn with it. Instead, it remained fixed in space, causing the train to tip over and derail. To solve this, Brennan introduced a second gyroscope spinning in the opposite direction. Both gyros were linked by a gear mechanism, ensuring that when one precessed, the other counteracted it. This allowed the gyros to rotate with the train, while cancelling out unwanted precession. With this problem solved, Brennan moved on to building a full-scale prototype that could carry real passengers. The prototype was 12 meters long and weighed 22 tons, with two massive gyroscopes spinning at 3,500 RPM, but scaling up the design created a new challenge. The gyroscopes weren't just fighting their own movement anymore. They had to counteract the weight of the entire train, which constantly tried to tip it over. While this wasn't an issue in the smaller model, the full-sized train required much stronger gyroscopes to stay upright. One day, while having lunch, Brennan received a mysterious letter containing the solution to his problem. Just kidding, that never happened. The real breakthrough came when he realized that controlling the gyro's precession speed could create a much stronger balancing force. To achieve this, he connected the gyros to a petrol engine and enclosed them in vacuum-sealed casings to minimize friction. Even if power failed, the gyros would continue spinning for 30 minutes, keeping the train upright long enough for it to stop safely. He then mounted them on a single gimbal, allowing the entire system to rotate freely along the train's roll axis. The gyro's axles extended out of their casings and made contact with guide plates attached to the chassis. If the train tilted, the axles rolled against these plates, increasing the precession speed and pushing the train back to equilibrium. However, this system had a flaw. Vibrations caused inconsistent contact, leading to unsteady corrections. Brennan refined the design by removing the guide plates and implementing an even smarter solution. He fixed the gyros directly to the train chassis so they would rotate along with it. Now, when the train tilted, the natural precession of the gyros activated a mechanical actuator arm. This arm was connected to valves controlling compressed airflow, which powered a pneumatic system inside a central tube. Inside this tube was a gear rack positioned between the two gyros. When the train leaned, the actuator closed one valve, directing compressed air into one side of the tube. This increased the pressure, forcing the gear rack to shift and rotate the gyros in the opposite direction, restoring balance. The key to this mechanism was that the compressed air multiplied the force, allowing a small precessional movement to generate a much stronger stabilizing effect. This ensured that the train would instantly correct itself before it could lean too far. The system was so effective that even if all passengers stood on one side, the train would remain perfectly level. Brennan's monorail was an engineering marvel, and its prototype was a resounding success. At the time, it truly seemed like the future of rail transport. However, investors were hesitant. Two rail trains were already well established, and implementing Brennan's monorail meant every carriage would require its own gyroscope, making it an expensive investment. Ultimately, this led to the project's abandonment. Despite this, the Brennan Monorail remains a fascinating piece of history, showcasing the genius behind its creation. Like the video and leave a comment sharing your thoughts on Brennan's design. Thank you for watching 4M Explain, and I'll see you in the next video.